The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, and welcome to this live learning event entitled Value Engineering with Injection Grouts, technology you can specify, control, and improve outcomes. My name is Don Rigby, Head of Marketing and Education for Avanti International, and today I get to introduce you to some pretty savvy people and facilitate a session to maximize the next 59 minutes for you. Engineers seek more than to specify products and procedures for their clients. They desire better solutions than any other engineered recommendation. Enter value engineering, a collaborative process whereby knowledgeable consultants, technology vendors, and experienced contractors coalesce the optimum solution based on conditions, objectives, economics, and longevity. Today, our highest objective is to discuss value engineering as it relates to injection grouts to control groundwater and improve soil conditions for geotechnical, industrial, and municipal applications. That's a tall order, and we need your assistance to make this learning session meaningful. The platform we're using has all participants on mute, but it's important we are interactive, and here's how. In the last 10 minutes, we've reserved it for questions submitted online, and I recommend as questions come to mind, immediately type them into the collapsible dialog box on the right of your screen. If we don't get to all the questions on this webcast, we'll answer every question individually by email, and that's a promise. The second interactive mechanism is poll questions. And these are interesting because we'll play back the answers right away, and you can see how your opinions stack up with your contemporaries. In many ways, these questions will lead the presentation. So let's do the first one right now. And if I can multitask, I'll see about launching the very first one. It should be launched. This reads, your interest in injection grouting is primarily for what market? Municipal, commercial, industrial, geotechnical, or all the above? Answers are pouring in, pouring in. In a moment, I'm going to close it and share the results. Closing now and sharing. Municipalities are winning the race here. Interesting. Interesting. All the above, 28%. Okay. Presenters, please take note because this is important audience mix. So allow me to introduce to you our experts today. All are engineers with deep experience in geotechnical, industrial, and or municipal applications. Brad Crenshaw is General Manager of Ground Engineering Contractors based in Knoxville, Tennessee. He's an engineer and geologist, invested primarily in mining and heavy civil construction industries with direct involvement in all methods of grouting. Brent Anderson is President of DBA Associates in Minnesota, an independent consultancy, and a team leader for Structural Group, a multinational engineering support company providing design, spec assistance, and construction services for public and private enterprises. Britt Babcock is a civil engineer with a geotechnical emphasis and heads up the geotechnical division for Avanti, and recently recognized as Vice President. He's a road warrior, investing half his time on job sites and contractors, and the other half with engineers, working on job specifications for both chemical and cementitious grout. And to start off with, I'd like for Britt to begin the first segment, providing a fundamental background on injection grouts, and then focus on municipal applications. And Britt, I will make you presenter right now.
Thank you, Don. I'd like to start with talking about what the goals are for grouting, and they basically fall into two particular arenas. One is to control the inflow of groundwater, and the second is to stabilize soils and rock. And how we do that is through the use of various types of grouts. And there's three predominant that fall within that category. The first are particulate grouts, or what we all know as cement grouts. Within that family, we have ordinary Portland cement and ultrafine cement, which is a cementitious type grout. Well, then we fall into the solution grouts family, or better known as the chemical grouts, with urethanes as well as acrylics and silicates. And bitumen is a hot tar type grout that's used for stopping large inflows. Definitely worth mentioning. It's a case-by-case basis and very specific use in those situations. I'm predominantly going to talk about, though, the particulate grouts and the solution grouts in this portion of the presentation. Where are grouts used? Well, municipal infrastructure is definitely a strong application for grouts, as well as all these listed here: mines, slopes and shafts, concrete and earthen dams, below-grade structures, waste encapsulation, soil-bearing improvement, specialty geotech, subways and tunnels, and structural lifting. I'd like to begin talking about the cementitious grouts mentioned just a second ago. What are the differences between a Portland cement and that of a cementitious grout or an ultrafine or a microfine? Portland cement, on average, has 15 to 20 micron size particulates within that mix or grout, whereas in the cementitious grouts, a microfine has an average of 8 micron particulates, and the particulates in the ultrafine is an average of 3 microns. Well, what does that mean to you? This is a scale of what the size of an average human hair is, of 70 microns, and that of a Portland cement, if you would very much associate with the size of a ragweed. If you take this micron, this 1 micron, and make it times 3 in size, that'll give you an idea of scale of how much smaller an ultrafine particulate is in comparison to its counterparts of a microfine or that of a Portland cement. What makes up a cementitious grout? Well, it's two components. You have Portland cement and a pozzolan. There obviously is additional additives for each particular mix design. Super plasticizer or water reducer is another way to coin that as a frequent addition that's used to help with fluidity. But the pozzolans play a key role, and there's two predominant types of pozzolans used. So there's a natural occurring pozzolan called pumice, which is what's used in a lot of ultrafine, and there's also a man-made pozzolan called slag. Slag is a byproduct of the steel process. Pumice is a byproduct of volcanic activity. Pumice definitely is a long-lasting pozzolan. I want to point this out, that similar cementitious reactions and components were used back in the early days of Greek, when you have the, here's a photo of the aqueduct, and still standing over 2,000 years ago. Some of the value adds for ultrafine cements that we see for those mixes is you have a variety of ranges of water cement ratios, from as low as 0.5 to 1 to as high as 8 to 1 in some parts of the country. Compressive strengths can range as high as 5,000 psi to as low as 100 psi compressive strength. The properties for a low water cement ratio, that's going to equal a high strength or a rock-like finished grout, whereas high water cement ratios are going to equal low strength or a soil-like grout. Moving on to the types of chemical grouts, two predominant families that are used throughout the industry are polyurethane and chemically activated. Within the polyurethane family, we have the hydrophilic foams and the hydrophobic foams. The hydrophilic foams have a strong affinity for water. They like to be in a water environment. Whereas the hydrophobic foam have little or no affinity to water. They can withstand the wet-dry cycles that may occur on projects. Typical of the urethane foams, they have a wide range of viscosities, as low as 50 centipoise to as high as 3,000 centipoise. Reaction times can vary from a few seconds upwards to 30 to 45 seconds and sometimes a couple of minutes. And they can be sensitive to temperature. They have a wide range of varying expansion rates depending on the product you might use, as low as 400 and to as high as 2,000%. Some of the value adds of polyurethane foams are single and dual component options. They can cure, or the cures can be accelerated Again, varying expansion rates of 400 to 2,000%. A lot are very chemically resistant, and there's several options in the marketplace for potable water certified products. Moving on to chemically activated gels. Within that family are acrylamides, acrylics, and silicates. Chemically activated gels are water-based, making them a hydrophilic. They like in nature. They often have ultra-low viscosities with the ability to penetrate very fine cracks in soils. Acrylamide with a viscosity of 1 to 2 centipoise. Acrylics is 3 to 4 centipoise, and silicates 5 to 7 centipoise. Some of the value adds for the chemically activated gels, lifespan, acrylamide upwards to 362 years, acrylates 54 years, and silicates considered a temporary solution on most applications at 1 to 2 years. Chemically activated gels are chemically resistant, and they have controllable set times as well, with the acrylamides and acrylates from a few seconds upwards to 10 hours, and then within the sodium silicates, about an hour. There are root control additives that are used in the municipal industry that can give you 2 to 3 years of inhibitor. Now moving on to municipal grouting. Municipal grouting is a key solution in controlling infiltration in the different infrastructure of a sanitary sewer system within a municipality. That sanitary sewer system will consist of a main line, laterals, manholes. Each one of these, whether they're joints in the main line or cracks in the main line, or at the connection points between the main line and the lateral, or the same joints and cracks and manholes, can serve as potential infiltration points. So how do we solve this with grouting? Sewer pipe joint sealing or grouting can be done with a truck and a packer. They'll straddle that joint and then pump grouts. They'll straddle the joint with the packer, pump grout in and around that joint, creating a bulb outside of the joint. You'll see here is an example of an excavated grout ring that was injected around a sanitary sewer pipe. So it creates a soil gel matrix, which is watertight. Again, pipeliners don't stop infiltration. That's another point of potential inflow or infiltration of the sanitary sewer mains. Again, that solution is grouting. They'll have a packer with a bladder that it can stand up into that lateral, and then the ability to inject a grout into all of those inflow or infiltration points. Manholes, again, curtain grouting of manholes are key, or crack injection for controlling water inflows and infiltration. Frequently done with chemical grouts. In this particular situation, urethanes oftentimes are used, whereas in sanitary sewer mains and laterals, acrylics are used most often. Grouting is truly a cost-effective solution. Quick example of pipe rehabilitation on 8-inch pipe. Pipe grouting, roughly $6 to $9 per lineal foot in cost, whereas in a pipe lining of that equivalent diameter, as high as $25 to $35 per foot. Lateral rehabilitation, connection grouting could be as high as $300 to $350 per connection, but that's minimal in comparison to what it would cost to replace that connection or do other means of repair or rehabilitation, ranging as high as $1,500 to $7,000 each.
Brent, thank you for that. I'm now going to make Brent presenter, and Brent, if you'll acknowledge, show your screen, I'll ask you to proceed.
All right, thank you, Don. Basically, what we're going to talk a little bit now are the variety of different types of techniques for solving moisture problems. And there's basically two classic approaches for below-grade waterproofing. There are positive side treatments, which are shown on the left-hand side of the screen. These are typically membranes that are in direct contact with hydrostatic water, and these are kind of classic positive side membranes that we use all the time. And then on the other side of the screen, on the right-hand side, a typical solution when a structure may have had a positive membrane and has started to leak, or sometimes even in new construction, we use negative side treatments. And basically, negative side treatment means that the membrane system or treatment is opposite the hydrostatic water. So these are the two classic ways we do water control, positive and negative side treatments. Now, when we get into negative side systems, there are basically 4 classic techniques that are used today. The first one and the most common one is injection grouting, seen on the upper left. Then there's a concept called water management, which basically you allow water to leak into the structure. You put a plastic membrane over the floor and wall, cover that with concrete or steel studs and gypsum, and then you direct that water to a sump and it's pumped back out. So in some respects you might think, well, that doesn't seem like waterproofing. Well, that's why we call it water management. And many times in water management, the first thing we do is we do injection grouting before we do the water management technique. Then there's coatings. Coatings typically are techniques where you put some type of chemically reactive or sometimes an elastomeric coating on the inside of the structure to seal out the water. Normally in coatings, we first inject all the active leaking cracks and joints. And then the last technique that is used on occasion is called electroosmosis. And this is basically an electrical solution, whereas what we do, it's shown in red here, we put small anodes in the cracks and joints on the inside face of the concrete, and then we put cathodes, rods that are drilled through the floor or wall out into the soil about 10 feet, and we connect those to a power supply. So we have this power supply providing positive charge on the inside of the concrete, negative charge out in the soil, and we create a very low-level electric field, and we move particles from the anode to the cathode, and in thus doing, we dry the concrete out. Now this next slide basically shows a graph, if you will, of investment required versus performance and difficulty of solution. And the very low-cost solutions are always interior crack filling. They're maybe not very high performance, but they're very low cost, and they work from time to time if hydrostatic pressures are very low. Crack injection is probably at the next level, a fairly low-cost investment. Performance sometimes can be a little irregular depending on how tight the cracks are, how old the concrete is. And then we have interior coatings. Usually a little higher performance, but typically with interior coatings, you first have to do crack injection, and that's why it tends to be a little bit more expensive. Then there's drainage. Drainage, typically, first we do crack injection of all the leaking cracks and joints, and then we put these plastic membranes, a sump system, and cover up that drainage media. And then there's the electroosmotic pulse technology, a bit more expensive. And of course, the final solution is exterior membranes, and that would be the cost to dig the structure up and re-waterproof it. Now that actually is always one of the best solutions if it's readily accessible. Many times the outside membrane is not accessible and we have to do crack filling, crack injection, interior coatings, drainage, or electroosmotic pulse technology. Now we're going to focus on the injection techniques today because we only have a few minutes. And there's basically 3 different types of injection. There's surface mounted injection, there's backside grouting where you actually drill through the floor and the wall, and then the most common one is called interception grouting where you intercept the wall or the wall floor joint at about the center third, or you intercept cracks and leakage in the floor in the center third of the slab. So we're going to talk briefly about all 3 of those. One of the things that you do need to understand is that when you're going to inject any type of grout into a crack or joint in concrete to make it monolithic, you have to understand that many times these cracked sidewalls are contaminated with clays, with silts, with carbonates, with a whole variety of different types of material. So if you have a structure that's been leaking for a long time, the cracked sidewalls may be contaminated, and anything that you try and inject in there is really not going to bond that well. It'll give you some some fairly immediate surface sealing, but with time, if the cracked sidewalls are contaminated, it's not going to be 100% solution. Another thing that's also very important, and we'll talk a little bit later, is that the pH of the liquid in the crack. There are many types of grouts that are not very resistant to super high pH environments, i.e. many times urethane type technologies. And in conditions where you have very high pH environments, typically we're looking at acrylamides and acrylates. Sometimes corrosion of steel byproducts are in the crack, and that can be difficult. And sometimes we have shadows, little voids that run behind the steel or under the steel where water can migrate as well. So let's look at the surface-mounted injection. Typically, it's a low-pressure technique where we put ports on the surface, and we either use epoxy or a two-part urethane, and we push that grout back through the crack and try and make the concrete monolithic. Here's an example of that. This is an industrial wastewater treatment tank where we did surface-mounted ports, and then we pumped a two-part urethane injection grout in all of the cracks to create a seal. Now at the bottom there, I go difficult to seal contaminated cracks. Many times in these wastewater tanks, there's a lot of sludge and debris in the cracks, so you do not always get 100% seals. Normally, if you can get 90% or better, you're doing pretty good. Interception grouting is the technique that I said is probably the most common, where you try and drill into the center third of the wall or the center third of the floor. Typically, we're injecting under pressures of about 100 to 3,000 psi. Normally, we don't like to inject any grout in concrete over about 400 or 500 psi because you're exceeding the tensile strength of the grout. So that means that using grouts with very low viscosities, as Britt talked about, is very important. In the interception grouting, we typically will inject hydrophilic urethanes, hydrophobic urethanes, acrylamides, polyacrylates, and occasionally we see situations where we may inject a microfine cement. So essentially, we're intercepting the center third of the concrete, grouting the entire crackage joint, and trying to make that concrete monolithic again. Now I show this next picture. Be careful where you drill. And remember, if this is a 4-foot thick slab and you see all the mechanical and electrical in this slab, if this were solid concrete and you couldn't see any of this and there were leaks, you certainly would want to do a ground penetrating radar to look at the areas that you're going to grout to make sure that you didn't drill into any piping or electrical conduits and create a bigger problem than what you already had. This next picture is some grouting that's being done at the World Trade Center. Here we're drilling and injecting into the wall floor joint, and you can see we're using a polyacrylate grout. So this is actually a two-component grout. If you look closely, you'll see a blue line and a black line, hoses going to the mixing head, and we have a acrylic resin with accelerator and a part B, water and a hardener. These are pumped 50-50. They're mixed in this mixing nozzle, and then it's being shot into the joint. Okay, the next example I want to show is using acrylamide, and this is a meat production facility, and the architect designed this with the processing area on the upper level and the storage of products on the lower level. And one of the things that was done is that they value engineered the waterproofing membrane out of this intermediate floor when they built this structure. So here's an example of the upper level. Here you can see the acid brick floor, and they value engineered the waterproofing membrane out. And what they did is they put 2 layers of 10 mil poly into this composite and decided that that would be their water control system. So you can see here we have acid brick floor, we have sloped concrete topping. The green is a layer of 10 mil poly. We have 2 layers of 2-inch polystyrene insulation, a layer of 10 mil poly, and then concrete with a steel composite deck. Well, to say the least, this structure leaked. And of course, water was leaking from the process area down on finished goods. The FDA inspector shut down the facility, and they were told that they had to correct this. Well, what happened was they were looking at removing the acid brick floor and the entire composite, and that was about $126 a square foot, and it was going to shut the facility down for several months. We come up with a plan to use acrylamide grout, which is very resistant to acids and chemicals, and we went with a 20% solution, which is about twice the normal concentration for acrylamide. And on the picture on the right, you can see we're starting to grout through the floor. We actually core drilled through the floor and about a 3 to 5 foot spacing, and we put an acrylamide grout in between the two layers of 10 mil poly to actually make the insulation layer a monolithic membrane. Here you can see in this picture we pumped at about 1 to 3 psi. We had set times of 2 to 5 minutes, a 20% grout concentration, and this grouting cost about $36 a square foot. To remove and replace all this, the floor and the structure within cost $126 a square foot. So it was a very cost-effective solution. On this next picture, we're going to a little different type of design. We have a granite panel system supported by masonry. This is out on a plaza. So this is a big earth-covered plaza, and water was leaking through the caulk joints into the void space underneath the granite panels above the masonry, and water was running all over the structure. So they looked at tearing this entire thing apart and redoing it. We decided to use hydrophobic grout at 20 parts urethane to 1 part water, a twin stream application, and we basically used a rigid foam grout to seal all the void space within the structure. And in so doing, we used this rocker arm pump. It's a 3-cylinder pump with an adjustable rocker arm, and we can use, by adjusting the rocker arm, we can do 1-to-1 ratio, typically hydrophilic grouts, up to a 20-to-1 ratio using hydrophobic grouts. That's 20 parts urethane to 1 part water. Here's a little better example how we put a stainless steel needle on the end of our grout line. We have a mixing chamber that you see there, and then we have the water coming in 1 part and the 20 parts urethane. So we get about 95%, our matrix is 95% urethane, about 5% water, and they're mixing before they actually get into the structure. That way we have good mixing capability of the urethane with water. So that's another good example of interception grouting. Now I'm going to talk briefly about backside grouting. This is where you typically drill completely through the structure and you pump grout curtains, if you will, behind the wall or behind the slab. So basically we're solidifying the soil and creating a curtain behind the wall or floor. Here's an example where we're core drilling right next to an expansion joint, and then we're going to create a grout curtain underneath this expansion joint to create a seal. On the right, we're hammer drilling through the slab, and we're doing grout curtains at about a 4-foot grid underneath this entire slab. Here we're using a hydrophilic urethane at 10 parts water to 1 part urethane. So this is a very cost-effective technique for doing curtain grouting. And then in kind of closing in this segment, interior coatings and penetrants, as I said, are many times used. Typically we need to grout the cracks first. Occasionally we do water management and drainage techniques, which I briefly described. We put a plastic dimpled membrane on the wall, on the floor. We pour concrete over it, or we build steel studs and gypsum sheathing. We collect that water at a sump, and then it's pumped back out. Here's an example of a project where we started out, and you can see the groundwater table, and this is a tunnel that's a people mover tunnel in Minneapolis, Minnesota, and groundwater was leaking up through the rocks and interfering with the water-cement ratio when they were trying to place concrete. So we put together a proposal to grout all the cracks in the rock and that was about $18.50 a square foot. And ultimately, what we did on this project on phase 1 was the grouting. On phase 2, they said, hey, are there some other things that you could consider? On phase 2, we did a water management technique where we actually put a dimpled sheet, a very strong dimpled sheet, over the rock, and then did our steel and concrete and our formwork on top, and that cost about $4.25. So there was a case where a sheet membrane for grouting was very cost effective. And then the last technique I said is electro-osmotic pulse technology. I briefly described this earlier, and this is a electric solution. It uses very low energy, but a way to dry concrete out. Thank you.
Brent, well said. And I'll now turn the presentation over to Brad and ask you to take on the next handful of moments.
Okay, thanks, Don. Our geotechnical presentation is going to be a little bit different than the previous two. They kind of had some nice pictures that they knew exactly what they were grouting into. Geotechnical is different. The ground is not an engineered material, so we have a different consideration, and our first consideration is always the ground. So obviously, we want to know whatever we can about the ground to first get a handle on things, and we'll probably know the rock top. If we are really lucky, then maybe we get some test values for leusions, the hydraulic conductivity of the rock, how good they are, sometimes questionable, but we try to use those to come up with a way to determine what grout we should use. The picture on the left over here could be tough ground, but actually we ended up grouting it off with the top 1-2 successfully. The picture on the right, we should be able to put any grout we want to into that ground, but it kind of lied to us a little bit, and we had to ultimately go with acrylamide to be able to get the ground to take any grout. So another aspect that you've got to remember whenever you're dealing with the ground is that it changes. The picture, these two pictures are for the same project. The picture on the left is at a depth of about 380 feet below ground. Ultrafine cement grouted that off just fine. The picture on the right is 40 foot deeper. However, it would not accept ultrafine, so we had to switch to acrylamide to get the ground to take anything. And finally, and probably one of the most important things with geotech, is that you've got to expect the unexpected. A good geotech investigation, it should give us a warm, fuzzy feeling to know that we can classify and predict probably 95% of what's in the ground. But what we have to remember with that is that means there's 5% we're probably never going to know. So a lot of times that 5% is what's going to be what we have to deal with as far as changes go. So my argument would be that the first value that we can offer as geotechnical practitioners is a thorough understanding of the ground and realizing what the ground can be. The rest of the presentation will kind of define some other things that we can add. And ultimately, what we want to do with a value engineering project is have a successful project. The little animation there, it wasn't just for fun. This hole is kind of an example of it, where we had a project where we had grouted this hole here multiple times and didn't achieve the result that we wanted. So we kind of came together as a project team and figured out a solution that worked on this hole and ultimately worked on multiple holes on the project. So I think that being said, the first thing that you need to do is put together the proper team. The problem with this slide is that I don't have any answers to go with any of these questions, and I don't necessarily know how to tell you to put together the proper team. I think that the takeaway from this slide is really, if you're going to be a grout purchaser, you're an owner or a GC, is read these questions and decide, can I do this myself? And some purchasers will be able to, or do I need to seek outside help? Because that outside help, what their real value may be is just to be able to assemble a team who can get the project done the correct way. So we talked about a successful project. I think it's really important to define what a successful project is. the first thing that I want to do whenever I get a call or walk onto a grouting project is say, why are we grouting? And sometimes the answer to that may surprise you. And really, sometimes the answer, whenever you get the answer, then you may have to say, well, grouting's not the right solution, or grouting's not going to get you to the goal that you want to achieve. And really, helping somebody find the right solution, whether it's grouting or not, adds as much value as anything, even if it's not adding revenue to your bottom line. The next thing is, if you're going to grout, then you need to be able to define an acceptable range of results that achieves that goal. So define what the results should be, and then do we have a range that will get us to our ultimate goal? And going on from that, then I kind of define this as grouting wants versus grouting needs. I can tell you, if I talk to someone who has not done a lot of grouting, when I ask them what they want to achieve with their grouting program, they're going to say a dry, fill in the blank, tunnel, mine, shaft, whatever it is. But really, that's not necessarily what they need. What they really need is to reduce the water to an acceptable level to achieve their goal, and they need that done at a reasonable price or schedule or whatever their main motivation is. So this graph is just theoretical. I put it together. It's not based off of any real numbers, but the point is to demonstrate the effort required to achieve a certain amount of water cutoff in geotechnical grouting. And this is a very important concept for people to understand. The graph may move around some, the blue line may change, but ultimately what you can see from it is that you can achieve fairly good results on most projects with a reasonable amount of effort. But as you move toward this 100% water cutoff or dry, then your effort increases exponentially for what you're going to cut off. So really, another value that I think we can add is to understand that in most projects we should be working on this side of the graph. Now, I'm not saying that there's not projects where we work on the right side of the graph. However, the important thing is if we are working on the right side of the graph, understanding why we're doing it and being able to convey the implications to our client. And quickly here, this is basically the same graph as before. However, what I have done here is I've just dropped in some real numbers to let you see what it really looks like. This graph is made up, and what it actually is, it is the dollars to stop a gallon of water per minute flowing into a tunnel. And it's based off of numerous large tunneling projects that were done in one specific geology. And the important thing here is you can see that there's a reasonable effort to stop up to somewhere around 95% of the water. However, once you go past that percentage, then you really have diminishing returns. And finally, so we've gone through the process and we've put together a plan. We should be prepared to change that plan. I'm not going to read this upper portion, but look at the second paragraph. This is the actual terminology that is included in every work plan we submit. And I think that's a really important aspect of geotechnical grouting, to understand that you come up with the best plan that you can, but your contract, your procurement process needs to be set up to change that to address the conditions you actually encounter. So sort of in summary, then, geology, we need to be able to interpret it to the best of our ability, and it's going to dictate. If you're looking at buying a grouting project, understand if you can determine who your team should be or if you should bring other people on. Define the goal of the grouting, decide what the results will be, if there's acceptable range of results, and formulate a plan and be ready to adjust it. And with that, I will go to you, Don.
I think I just love the way you think, Brad. And before we go into case histories next, I'd like to launch one more survey real quick. It says you primarily specify injection grouts for the following. Check one, please. There is no wrong answer. And as always, I'll share the results in 5 more seconds. Okay. Closing survey. sharing survey. Voila, rehabilitation projects. There's our winner for the day. But that's what I expected. That's not far off. Okay, if I could ask then that you continue, Brad, and discuss some case histories that support this idea of value engineering.
Okay. Am I in control of it now, Don?
You are. I never took it away.
Gotcha. Okay, so what we're going to do is we're going to go through just a couple of projects here, and the goal is going to be to demonstrate some of the aspects that we talked about before, hit a few highlights. We aren't going to go into a lot of technical detail, but really what I want you to look at is there is a yellow bar at the top of the screen, and that is what I'm going to call the effort bar. And so whatever your effort is, whether it's money or it's time or what's important to you, then this just sort of takes us through the process of when we step onto a site and we implement these various sort of values that I've discussed and see how the effort changes based off of that. And this is relative, just sort of to typical projects. But so basically, this first one is inflow from a large inflow from a sinkhole. Large inflows can be sort of funny because depending on how complicated they are, they could be a really low effort or a really high effort. So it's sort of mid-range. The geology, as we said, affects it. So this is karstic, which can be complicated and could increase the effort that you need material-wise and cruising equipment. So, however, we get to talking with the quarry owner, and they don't need this quarry dry. Really, all they need to do is be able to pump the amount of water that's coming in. They're already pumping. They're already set up. So we don't have to stop all the water, which reduces the effort. And finally, as we're talking to them, they may not be mining this area in 10 or 15 years or 5 years. So they don't have to have a seal that's going to be permanent. They can accept a temporary seal, and if they need to deal with it again in 5 years, then they can deal with it. So it really brings the effort down. White Oak Resources is a decline. They were coming up on a zone that could have high potential inflow, so they needed to do something to decrease the chances of the water coming in. So a sort of typical job. However, they are dealing in a sandstone layer that's fairly notorious for requiring a high amount of effort to stop the water, which drives the effort up. However, they don't need this dry. They just need to get it at a condition where they can get through this 400-foot zone, which brings the effort down some. And acceptable is safe for their personnel and equipment, doesn't have to be dry, so basically very similar to their goal. Finally, this is a shaft in Kentucky, a raised bore shaft. When they drilled the pilot hole, they had a large inflow into the hole. This typically can be a fairly easy solution if it's isolated. It's complicated a little bit because the pilot hole is already there, and you need to save the pilot hole. But again, they're dealing with one of these sedimentary type formations that requires a fairly significant amount of effort to grout off. So the effort jumps up there. You talk to them, and what would they like to have? They'd like to have as little water as possible, so a fairly significant amount of effort. However, after you really start discussing it with them, and they talk to their operations people and their underground people, then they can be set up to accept up to 100 gallons per minute of water coming into this shaft, which really reduces the amount of effort that you have to put into it. So in summary, as geotechnical grouters, where do we add value? We understand the geology. That's always the basis. We really aid in helping our clients define a goal for their grouting, and once we understand that goal, we clarify what their results need to be, and a lot of times we can bracket those, and we help them understand what the cost-benefit ratio of the lower and the upper end are, and then finally we come up with a plan and change it as necessary. And that's the end, Don, so I'll go back to you.
Perfect. I'm going to move over to Brent. And Brent, you gave us some case histories already, but I'd like for you to share a few more. And I love how you think as well. Fire away.
All right, thank you very much. I just need to
Slide down to get that other. There you go.
Yeah. I thought I
Sneaks up
had
on you,
this.
doesn't it?
Yeah, I thought I had this already preset.
You'll enlarge your screen, you're in business.
Yep.
Whoops.
Do we look? There we
There you
go.
go.
Okay, as Don had mentioned earlier, one of my jobs is I'm the geotechnical and moisture control consultant for Structural Group. We have 21 branches around the United States. We do construction work for all types of moisture control in industry, in commercial, and in the industrial environment. I'm going to just do a brief discussion, a little bit more detail on backside and curtain wall grouting, a very common process that's used. And this project that I'm showing is in San Diego, California. The Pacific Highway runs here, a very busy freeway in Southern California. And you can see there's an exit ramp that goes down and turns and goes underneath the highway. And then the Pacific Ocean is about 500 yards away. So this area is influenced by tidal activity. And about halfway down this ramp, we're at groundwater table, and this whole section here is below the groundwater. I have these two tanks shown here. They've now since been removed, but these tanks had chemicals in them, very harsh chemicals that over time had leaked and contaminated this whole area. So as water was leaking in this ramp area, the surface water was going to a drain and going out into the bay. So we're going to talk about this area here. This is called the Witherby Street project, and this is a new housing area. So what happened here is they added electrical high voltage lines under the road. It ran down the ramp and then continued on to provide power into this housing area. So the next slide gives you a flavor. They have this slab, and this is designed to resist hydrostatic water. On this slab is 8 feet thick, and what they did is they cut about 5 feet into that slab to put these high voltage lines. And so this next picture kind of shows a little better example. This is where those high voltage lines are placed in the exit entrance ramp, and you can see water leakage is coming up through these joints. There's been a lot of seismic activity and continues to be. That water is collected in these little trenches, and it runs to a collection point, and then it's actually pumped down here into these tanks. And we're getting about a gallon per minute, 500 gallons per day, and about 45,000 gallons a month of water that's contaminated that has to be treated. That's a very, very expensive proposition for the utility. Here you can kind of see some of the trenches that were cut in. Basically a water management technique where they collect the water and then they pumped it into tanks and then they had to treat it. Here again are some more pictures of the construction work. You can see the high voltage lines being placed. They put some gravel fill on there, and then you can see that they poured the concrete back on top. And due to seismic activity and movement, little cracks developed, and then this area really started to leak pretty bad. The owner hired over a period of a couple years 3 different contractors that proposed hydrophobic urethanes. One proposed hydrophilic urethane, and another proposed a 2-part urethane. All of those systems lasted about 3 to 6 months, and then leakage continued. Part of it probably because they tried to inject the cracks and seal them rather than maybe trying to do a curtain. So what we basically proposed, and you can kind of see the evidence of the water here and how it was leaking, we proposed to do backside grouting where we put a curtain, about a 6-inch thick curtain of grout underneath the whole area. This picture kind of shows in plan, this red represents the utility, and this is about 8 feet across. So what we ultimately did is did our port spacings about 8 feet on center, so when we're grouting and this grout migrates out, at about 8 feet we should get transition of grout across and underneath this area where they worked. This blue area shows a zone where they actually chipped out 28 inches of concrete, put in a membrane, and put the concrete back, and that lasted about 7 years, and then that started to leak. So here we are, core drilling on the outside of that 8-foot trench, and while we were working, 3 of the 6 lines were always active, so we had to do this work while there was energy going through the system. We're doing a little interception grouting here at the joint, and in these we used a 30% acrylamide solution, a real concentrated solution of acrylamide. Here's a core that we took out of that area where they actually took 28 inches of concrete off the top, put a membrane, and then, as I said, that lasted about 5 to 7 years, and then it re-leaked. Here we are mixing up some of the acrylic resin. These are the pumps. These are piston-driven, one-to-one pumps that I use. Many times we'll pump 2 ports at a time, and I got these 2 pumps in unison. Here we're injecting through grout pipes, and you can see in the background here some 6-foot grout pipes and some 5-foot grout pipes. These were put down the 3-inch core holes, and basically we injected in the top, and the grout comes out the bottom. This little black area is that rubber gasket that when we tighten the top forms a seal. And then just to give you a little flavor, we did this work December 3rd through the 8th, so it's about 6 days. We were pumping about 700 gallons per day. This tells you how many ports. And we lost actually 2 ports, so we couldn't get them out of the cores, but all the rest of them we got out in renews. We had pHs. Our A side was about 9. Our B side was 3.7. And then our set times were about 30 seconds to 45 seconds. At the end, we sealed this area up. It's went through a lot of seismic activity. It's about 5 years old now and has never leaked again. So the utility company is extremely happy with us doing this backside grouting technique. Thank you.
I think that's a great proof statement for injection grouting. Thank you for that. Britt, I'm making you presenter.
Thank you, Don. Now to move on to some municipal case studies. I have 2 I want to share with the group. The first is the city of Sunrise, Florida. The city of Sunrise, Florida, located in a floodplain there, had some infiltration issues that they solved through mainline grouting with mainline grouting and sanitary sewer using acrylamide grouts. I apologize, this project's not in a floodplain, so I want to correct that. That was a mistake on my part. But they were challenged with pretty significant inflows that were very costly to them. And what I want to share with you is the measured inflows that the city of Sunrise were experiencing was up to 720,000 gallons per day. They did choose to use acrylamide grout to cure or to grout that mainline joints. They grouted 500 lineal feet of 12-inch sewer. The cost to grout that was approximately $24,000. That grout resulted in a flow rate reduction of 615,000 gallons per day, roughly a savings of $1,328 per day, or just more than $2 per 1,000 gallons. Pretty significant savings based on that one single line of 720,000 gallons per day. That to treat that flow would have been just almost $485,000 minus the installation cost, resulted in roughly $460,000, $461,000 per year in savings to the municipality just to treat that I&I. The second project I want to share is Granite City, Illinois. Now this project is located in a flood basin. And what they were challenged with were fluctuating groundwater that impacted the sanitary sewer system. And in this particular instance, this is a large diameter system of 108 inch. You'll see in this photo there's slumping pavement, and they experienced this in many cases throughout the city, many locations. What they found was seasonally fluctuating groundwater levels was the issue. And to quote an article out of underground construction, and one of the engineers on the project said that the fluctuation of groundwater fluctuations has had a drastic effect here, and sewer repairs have been needed for some time. high groundwater in the last years has created sewer failures, sinkholes, and even a few blocks of collapsed road. Pretty significant. So what they did, the solution was to come in and grout those joints and seal off that sewer line from the impact of those fluctuating groundwater and the I&I that was occurring. You can see here in a 108-inch diameter sewer line, this is combined sewer, both storm and sanitary, given that's why the size. Metal frame here to create that seal and to inject that grout. Summary, it had 3,600 lineal feet of 108-inch diameter combined sewer pipe. They injected approximately 2,100 gallons per joint on a total of 600 total joints. The cost of the large diameter grouting program was about $366,000 or $610 per joint. And keep in mind, that was for 108-inch or 9 feet in diameter. What they found and what they believed and experienced was for large diameter pipes that are structurally sound, grouting is just as viable a solution. It's considered more economical. So a great couple of case studies that were very successful in the municipal industry.
Very good. And thank you for all presenters for sharing. Let me go full screen. Can you see my screen okay?
Yes.
All right. Something that Avanti is really particular about is in the announcements leading up to this event, we have itemized 6 takeaways that you would yield from this presentation. And above all else, we want to make sure that we deliver on this promise. So we talked about insight on how, when, and why to look beyond standard practices and procedures. We talked about unique cost value benefits, the life cycles of each grout type. Understand how to tailor set times, mix ratios, additives to satisfy specific needs based on site conditions. Differences between geotechnical, industrial, and municipal specifications. I think Brad did a great job on that. He did a great job as well on New Twist for procurement. That is clarifying goals and predetermining what is acceptable based on cost value. And then, of course, we walked into case histories, which I think are proof statements for municipal, industrial, and geotechnical applications. Let's leverage the next just a couple minutes we have remaining. And I am a stickler about time, guys, and we need to make these answers very crisp because it is near the top of the hour. So here's one question I've got to rifle out to one of you, and I'll tell you who it is in a minute. We have a project with 4 underground concrete vaults in high groundwater area. We're currently having problems keeping water out of these structures. What products would be appropriate for fixing this issue? And I'm going to go to Brent with that answer.
Okay. You know, I'm going to assume that the water is leaking through joints in the vault, potentially some cracks, but probably the floor-to-wall joints, some wall joints, and then potentially around the piping that comes through. And, you know, the first solution might be some interception grouting. If the cracks are real tight, I would suggest that you consider a high solids polyacrylate. If the cracks are larger, a hydrophobic urethane could possibly be a good solution. If the leakage is really problematic beyond that, you probably are going to need to do some curtain wall grouting, in other words, some backside grouting. And there I would consider using a acrylamide or a polyacrylate grout under the floor and behind the walls in all the areas in and around the piping that exists.
Thank you. I'm going to go to another question here, and I've got to make this one brief. What are the advantages and disadvantages to using different types of grout for a given application? And someone who's had a lot of experience with that is Brad. Brad, would you respond to that?
Quickly, I'd say that the advantages are that you're going to get more water cutoff because you're going to ultimately do a better job because you're going to fill up the bigger cracks or joints than the smaller ones. The disadvantage is simply probably going to be cost because you're going to have more equipment on site to handle the different types of grouts that you're injecting because you're going to use different equipment for different types of grouts.
Thank you, Brad. Britt, I got one for you here. And then I think I need to put the Q&A process to close. Please explain the decision process in choosing to use a hydrophilic, hydrophobic, and vice versa.
And you want me to answer that one?
I think, Britt, that's a question for Britt.
Oh, for Britt. Okay.
Thank you, Don. The question, to repeat, is when is the decision to use a hydrophilic versus a hydrophobic? Hydrophilics generally are single components that are water reactive. So oftentimes when we see a continued water source situation, hydrophilics tend to fit that bill and are used in those applications because you can just pump the grout in and it will react with the water and create that seal. And they're flexible. They come in various viscosities and can get into fine cracks or higher viscosities that can get into larger cracks and successfully seal those off. Hydrophobics often are used when the crack may be seasonally wet. There are flexible versions of the hydrophobics that can be injected into cracks that can then expand and contract with that crack movement, like Brent alluded to. But within a hydrophobic family, we also have rigid and semi-rigid grouts as well that oftentimes get used in void fill type applications. So just some slight variances between the two, and but definitely some unique applications where they can fit.
Thank you, Britt. As I suspected, we now have more questions than time, so I'll remind you, if we did not answer your question live, we'll answer it personally by email, and I trust you're okay with that. As we wrap up this presentation, let me remind you that within 24 hours, you'll receive 3 documents by email, including a white paper, published article, and case histories. And with these, we're extending the learning beyond this webinar. And speaking of that, for those who were requesting PDH credit for your participation here today, please email your request to jessica.williams@AvantiGrout.com. She'll confirm your participation for the full hour, including your post-survey comments, and issue a certificate. Folks, we love teaching what we know and believe about injection grouting. And the only thing that we enjoy more than webinars is teaching nose-to-nose, belly-to-belly. And there's a hands-on training opportunity at Avanti headquarters in Houston, Texas on March 11 through the 13th. This is our Industrial Geotechnical Injection School. The guest speakers you heard on this webinar will also be presenting at this school, as well as other folks, with a wealth of instruction on soils, methods, and hands-on workshops. Believe me, when I wind these 2 speakers up, 3 speakers up that you heard today, and I give them more time to elaborate and share more detail, you'll have an earful and a heartful. So you're encouraged to go to AvantiGrout.com and view this and other educational opportunities. I'll send you a link on that tomorrow. Let's segue to one more poll question, if we could. And I'm going to be real quick on this one. He says, and this says, from the family of injection grouts, which interests you the most? Cementitious grouts, polyurethane, acrylic grouts, or all the above? Answers coming in. Audience, you've been great. Thank you for your participation. Looks like I've got enough answers where I can close it and share the obvious, and that is your engineers. You want to know about all these things, and they're all appropriate given whatever application you're trying to solve. Your solutions people. Admire that. I'm going to go ahead and close that, and I'll ask presenters, care to make one more parting comment? Brad, I'll begin with you.
I'll just say thanks for the opportunity to let me do this, Don. I appreciate it, and I've enjoyed it. I hope everybody has something to take away from it. And I'll say this, it's a lot to cover in just an hour, so I encourage anybody that's interested to attend the school in March.
And Brent?
Well, as well, I would encourage anyone and everyone that can attend the grouting school, and certainly send your questions on to us, and we will work to develop answers. One of the things that I'll tell you right now, you got 3 engineers, Brad, Brent, and Britt, and you're sometimes going to get 3 answers that seem a little different, but potentially are quite similar. But we all have different ideas on how this is done, and certainly getting a wide variety of opinions on this is really good for you engineers to make decisions.
Absolutely. Thank you, Brent. Britt?
I just want to thank everybody's participation. I appreciate the privilege to speak to everyone, and just resonate with Brad and Brent say that a lot of information to try to cover in 60 minutes, and we just scratched the surface and look forward to the opportunity to communicate more with everybody on the call.
I have enjoyed working with you guys, Brad, Brent, and Britt, all starting with BR. That's been a problem for me. I don't know about anybody else. Look, as you exit this webinar, you'll be asked a few questions. If you feel you were well served over this last hour, let us know. We fully intend to be the best in the business, and with these live learning events, and your feedback will tell us how. For now, Avanti International says thank you so much. Until the next time, so long.